Let's say we have a pail of water here. It looks like this. It has a handle on it. There's the handle. And we got two people lifting that pail of water. We have one person in this direction and one person in that direction. We'll give the people some names here. Let's say we have Jack in this direction and we have Jill in that direction. Jack and Jill. The pail of water has a mass of 1.3 kilogram. Jack exerts a force. Where's Jack? We'll call this F1. His force has a value of 7 Newton. And Jill, we'll call her force F2, has a magnitude, a value of 11 Newton. I don't know the direction yet for either one. It says Jill force actually makes an angle of 28 degrees with the vertical. So if you draw a vertical line like this, this is 28 degrees for Jill. At what angle theta with respect to the vertical should Jack exert his force? So what's the angle theta here? This is theta. So let me write the question. Question 1, or A, at what angle theta with respect to the vertical I drew it with respect to the vertical, you can see it, should Jack exert his force to do what? For some reason, to do what? If the pail is, that's the key, if the pail of water is to accelerate straight upward, the word straight here becomes really important. I'll underline it. Upward. Maybe part B will do find the acceleration. Upward. I'm assuming that 1.3 kilogram, the way we stated, that's actually the bucket and the water that's in it. 1.3 kilogram combined. Otherwise, I have to give you how much water in it, what's the mass of the water, assuming that's the same, you know. Okay. That's the question. We have a bucket or a pail here. It has the mass of it with the water at 1.3 kilogram. Two people holding it, they're going to move it upward, straight upward. And the question, what do you think the angle theta should be for that bucket to move straight upward? And the other part is, what is the acceleration? I need to do my free body diagram. here is what we know. We know the weight down, the weight of the pail. Right? And what is the weight? Weight equals mass times gravity, right? What is the mass? 1.30. And what's gravity? 9.8. So 1.30 times 9.8, which is 12.74. How about 12.7 kilogram? It's probably 12.8 if I use 9.81, but that's fine. What else we know? I know there is a force in this direction. That's F2. The value of that is 11 Newton. And I like this angle. Let me call this angle what? If this is 28, 28, what is this angle down here? 62, good. Because I like the angle with respect to the x-axis. So this way, the x component will be the cosine, the y component will be what? The sine. I have another one. We'll call it F1, and this is theta. We don't know what that angle here is. So if this is theta, this is really 90 minus theta, but let me call it alpha. Because if I know one, I know the other one. If I know what alpha is, can I find theta? That might be easier if I do them that way. I could still use the 28 in theta, but you have to think backward. If you decide to use the 28 in theta, then the x value will be in that direction, and that becomes the sine instead of the cosine, because you're using the angle with respect to the y-axis. If you stick with the angle with respect to the x-axis, the way we've been doing them, then the x is always the cosine, the y is always the sine. That's the reason why I'm asking for these angles. So I don't want you to think backward, like, oh, why is he switching? The x value is the sine, the y value is the cosine. But I could have stayed with it. Yes?
Is the 12.7 supposed to be newtons or?
Newtons, thank you. Yep, that's the weight. So now let's take each vector and break it down to x and y component. Here's my free body diagram. We have the weight down, 12.7 Newton. I'm going to take F2, and notice F2, to go from here to there, you have to go to the right, then go up. To the right and up. So it's going to have a component to the right and a component up. The one to the right is going to be what? 11 cosine the 62. And the one up is going to be what? 11 sine 62.
I have a question.
Yes.
Why are we using 62 instead of 28?
I'll answer that in a minute. 11 cosine 62. Because if you want to stick with x being the cosine, y being the sine, you always want the angle with respect to the x-axis.
Oh, got it.
But I could have used the other angle. I'll show you in a minute there too. Roughly 5.2 here, 1/6. And this one, 11 sine of 62, 9.7. The question, why did we use the 62 instead of the 28? If you wanted to use the 28, then this value here, it's really the opposite, because to get the x value to the right, that's to the right, notice that's opposite to this angle. You will have to use, for the bottom, instead of cosine, you will have to use 11 sine of the 28. And we've been saying x is always the cosine, y is always the sine. And this becomes 11 cosine the 28. And I bet you if I went to my calculator and I typed these numbers, watch this, 11 cosine 28, does that give me 9.7? Yep.
Yeah.
And if I did the 11 sine 28, does that give me the 5.2? 5.16, yep. So I could have used the other one, but then you have to change your thinking, saying the x value now is going to be the sine and the y value is going to be the cosine. So that's why I opted to switch them to find the angle with respect to x. So this way you don't have to switch your thinking.
So if the problem said respect to the horizontal, then we would do it like that?
Correct, that would be the 28 here. No, for 28, that would be the cosine 28. Because if the angle with respect to this line, x is always the cosine, y is always the sine. So when I look at this one, f1 now, notice if I use alpha, because alpha with respect to the x-axis, right? I need to go to the left, because you have to go to the left and go up to go from here to there. So this value in the x direction is going to be f1 cosine of alpha, because alpha with respect to the x-axis. And the y value will be what? f1 sine of alpha. So these are my forces now. I did the free body diagram. This is the FBD, free body diagram. I decide to take each vector, break it down to x and y component. Now let's see if I can answer the question. The first question says, at what angle theta? Well, I don't have theta, I have alpha. But the good news is if I know alpha, I can find theta. 90 minus alpha, right? They make 90 degrees. So let me focus instead of what angle theta, let me say what angle alpha. To find such that the pail is going to accelerate straight upward. What does that mean, straight upward? It didn't go left to right. It moved straight upward. Well, the fact it didn't go left or right, that tells me what? Exactly. The net force in the x direction is 0. All the forces to the right have to equal to the left, because if one was bigger, it's not going to go up and down. It's going to go to the left or to the right while it's going up and down. So that tells me that the force is pointing to the right. If you take all the forces to the right, should equal all the forces to the left. Again, that came from the word straight upward. That was the significance of that. It means the net forces in the x direction is 0. We have no net forces in the x direction. They cancel each other out. Up equals down. I mean, left equals right. So what do we have pointing to the right? The 5.2. What do we have pointing to the left? I forgot. F1 had a value. I forgot to put the value. What was the value for F1? 7, right? Let's put the 7 here. We know what that is. So what is the value to the left? That was given to us. The 7, that was in the problem. Yep. I just forgot to write it. What's cosine alpha equal to? 5.16 or 5.2 divided by 7, which is 0.74. And to get alpha, we take the inverse cosine. If you know the cosine, you want the angle, you have to use the shift key on your calculator. 0.74. And it's approximately what, 42 degree? Yeah, what, 42.3? So if you know alpha, can you find theta? Let's look back at the picture. If I know this angle is 42.3, can I find theta? So theta is going to be what? 90 minus that number, right? 90, not 9. It's 47.7. Now let's look at up and down and see what's going on there. Let's see what we have for up and down. Let me draw that picture again, put some numbers in it, instead of all the extra stuff that's clogging it. We have 12.7 down. We have 9.7 up. I don't care about left and right. I'm just talking about up and down. I can actually put them there. This is what, 9.7. We have 5.2 this way. And what is this value up and left? What are the values up and left? I mean up and down, or these two values here actually. Do we know what alpha is? 42.3, right? So can we get these numbers? 7 cosine 42.3. Go right here. 7 cosine 42.3. This number is 5.18 or 5.2. In the y direction, 7 sine of, what was it? 42.3. This is a 4.7. And notice the x values do cancel each other out. 5.2 to the left, 5.2 to the right. So
That's why it doesn't move.
Correct. That's why it moves upward. What about the y value? What is the net force in the y direction? Notice is what's the net force? I use y for y direction. Well, the net force, if we take the ones pointing upward, it looks like if you add them, it's more than the one down, right? So we have the 9.7 up, we have the 4.7 up, and we get the minus because that's pointing down to 12.7. Up is positive, down is negative. So the net force in the y direction equals 9.7 plus 4.7 minus 12.7. That's a result of 1.7. Since that value is not zero, I can use what? Newton's second law. It says the net force, it didn't say which direction, doesn't matter what direction, is equal to the mass times the acceleration. The net force is 1.7 Newton up. That's what the net force is. We're pointing upward. Should equal the mass of that pail, which is what, 1.3? Times the acceleration. And the acceleration will have to be the same direction as the net force, which means pointing which way? Upward. So my acceleration will be pointing upward, and the value of that is 1.7 divided by 1.3, which is 1.31. So the acceleration is 1.31 meters per second squared. Direction where? Upward. Let's try another one. Another example. What do we have? We have a 6 kilogram block of ice. Six-kilogram block of ice acted on by two forces, F1 and F2. So we have people pushing down on them. We have a force in this direction, we'll call it F2, at an angle of 30-degree angle here. We have another force in this direction, F1, at 60-degree angle. Let me give you values for F1, F2. If F1 is 13 Newton, F2 is 11 Newton. Let's say this actually ice is sitting on a table. Now when we say ice, the reason we use ice instead of something else, because ice simulates frictionless. So it's sitting on that table. You get two people pushing on it. There's probably a chance that ice is going to move one direction or another, left or right. It's not going to go up and down. The only way it will go down if you break that table. By pushing down, that table breaks will go through the table. Assuming the table is made out of steel, it's not going to break, that ice is not going to move up and down. It's going to move either left or to the right. We're not sure. And the questions are, tell me what the acceleration is. A, find the acceleration. B, find the normal force. These are my two questions. Free body diagram, here we go. I'm going to make the center of this is actually the box, the 6 kilogram. So this is the 6 kilogram right here. That little dot is your 6 kilogram. What are the forces? We have the weight straight down, right? Which equals 6 kilogram, the mass, times gravity. 6 times 9.8, it's what, 58.8? What else we got? We got F2, which is 11 Newton pushing in this direction. So if you look at it, it's coming like this. That's where F2 is going. It's pushing in that direction, right? If you're pushing on it. So this is F2, has a value of 11 Newton. And if this angle is 30 degrees, what's this angle here? Nope, if this is 30, what's this one? 30. It's the same two lines crossing each other. We also have, let me add the other force, F1, which is coming this way. Value of 13. And the angle is what? What's this angle? 60. So to clean it, looks like messy now a little bit there. I'll do one more free body diagram. And I left one more force out, by the way, I forgot. There's one more force, which is what? The normal force, and that's pointing which way? Upward. So here's what we know. We know the weight down. The weight, which is 58.8. We know the normal is upward. Now let's look at these two forces, F1, F2. F1 is pushing this way, so to go from here to there, you have to go to the left and where? Down. So it's going to have a component to the left and one down. And the one to the left is going to be what? 11 cosine, because x is always the cosine, right? And this is what? 11 sine 30. So let's use our calculator. 11 cosine, 11, not 1. 11 cosine of 30. 9.5. And in the y direction, 11 sine of 30 should be 5.5. 5.5. Now let's look at the other one. Has a value of 13. And what's the angle? 60. So to go this direction, you have to go to the right and down, right? It should have a component to the right and down. To the right will be what? 13 cosine 60. I think that's 6.5. I might be wrong. Cosine 60, 6.5. And in the y direction, it should be 13 sine of 60, almost a 9. Oh, 11, I'm sorry, not 9. 11.3. So these are all the forces acting on that. Is the block of ice moving up and down on that table? No. If it's not moving up and down on that table, that tells me the net force in the y direction has to be what? 0. The net force in the y direction has to be 0. What does that mean, the net force is 0? That means if you take all the forces pointing upward, should equal all the forces pointing which way? Down. What do we have pointing upward? We have just the normal. And what do we have pointing down? We got the 5.5, you can see it on the left, plus the 58.8 in the middle, plus the 11.3 on the right. 5.5 plus 58.8 plus 11.3. 75.6. So we just answered question B. Find the normal force. Question A, notice I see the force to the left is bigger than the force to the left. See, the force to the left is 9.5. To the right is what? 6.5. So you have a net force in the x direction. So what is the net force in the x direction? That's the 9.5 minus what? The 6.5. Which direction? Left. $9.5 minus the 6.5. I'm pathetic. I'm using a calculator for that. That's 3. That's the net force in the x direction. Well, Newton's second law says if you have a net force, then the net force should equal to the mass times the acceleration. That's Newton's second law. My net force is 3 Newton to the left. It should equal the mass, which is what? What was the mass of that? 6 kilogram times the acceleration. So the acceleration has to be 3 divided by 6, which is what? 0.5 meter per second squared. And it's always the same direction as the net force. So which direction the acceleration? Left. The block of ice will move to the left.
That's why you did 9.5 minus 6.5,
Correct.
right? Instead of 6.5 minus 9.5.
Well, if you did that, would be a negative value, yep, which means the direction is going to be the other way.
Okay.
Yep. So now we know which way the block of ice is going to move. We know the acceleration of it. If you want to use right is positive, left is negative, you can. And your acceleration in this case will be a negative value, which means going which direction? To the left. So you could still stick with right is positive and left is negative. If you did that, this would be a negative 9.5 plus 6.5. That's a negative 3. When you do the math, the acceleration will be negative. And we just said right is positive, left is negative. So if the value is negative, that means which way? Left. So you can still stick with the convention. Up is positive, down is negative, right is positive, left is negative, and do it that way. Let's do one more similar to these. Okay. Let's say we have a person, we'll give it some weight in a minute. I'll leave it without a weight even. We're going skiing. Here we go. So we have an angle theta here. And we have somebody's going skiing or on toboggan. You're taking your nephew and nieces on that toboggan there. So your niece now with the long, could be a nephew with the long hair. Has a mass m. Well, the mass is always for a person is pointing straight down. The mass always points straight down. That's where the weight is mass times gravity. The weight, I said the word mass, but it should be the weight is always pointing straight down. It's the mass of the person times gravity. Now let's say this angle is theta. I'm not giving you any numbers. I'll put numbers shortly. You put the person there, and what's going to happen? If there's no friction, that person is going to slide down, right? Can we come up with an equation for the acceleration? Well, which way the person is going to move? I know the person is going to slide or move in this direction. That's where it's going to move, right? If you're on a toboggan or on skis and it's frictionless there, you stay on a hill like this, you will slide that downward. So you're going to move in that direction. Now, also, since you're sitting on the slope or standing on the slope or the snow, the ground is pushing up on you. And I forgot to mention this part. The normal force always perpendicular to the surface, always. So your normal force, because we had a flat surface, everything we did so far. Now this is not flat. So your normal force is going to be 90 degrees with the surface. So your normal force in that direction. This is not a force. This is just a direction which way you're going to move. So maybe I'll make it a dotted line to let you know you're going to move. That's not a force. You're going to move in that direction. So you only have two forces acting on you. You get your weight down and the normal force in that direction. Now, if I extend the line here, if I extend this line through it at 90 degrees, this is 90 degree angle. Do we know what that angle is? Can we figure out what that angle is? We don't know. We don't know what that angle is. Let's say this is 20. Can you tell me what that angle is?
Same.
Sure, same. Why? Because this is 90 degrees. Right? If this is 20, what's that angle here? 70? That'll make this one 20. So this angle and this angle are the same angle. These two are exactly the same. So let me redraw. So my free body diagram, let me make this my x-axis now. See that line going through it? Let's make that my x-axis. What can I do to make it without making it really messy? Oh, maybe that will do it. Yellow highlighter, let's see if that will do it. See if you can see it. Let's say this is going to be my x-axis. I'm going to make this my x-axis. Can you see it? Can you see that yellow or no? X-axis. And this is my y-axis. X and Y. So what's my free body diagram looks like? If I do it right next to it, well, we like to draw the x-axis horizontal, right? We don't like them on an angle the way you see in that picture, and we like the y-axis this way. So what you're looking at is the normal force, which is straight up in the y direction. This is the normal. And let's look at this force. If this is my x-axis, that's my y-axis. See the x here? This is the y. This is quadrant 1. The weight in which quadrant? Quadrant 4th, and it makes a theta with the y-axis, right? So the weight is really in this direction. And this angle is theta. And notice theta is actually with respect to which axis? The y. So when you go to break that vector to x and y components, we need to remember this, what I wrote here. Where is it? Let me just pull my notes out. We need to remember this picture. If theta with respect to the y-axis, remember the 28 was with respect to the y, and the 62 was with respect to the x. So if I use that angle with respect to y, the x component, look what happened to it. It's not the cosine, it becomes what? The sine, and the y component becomes what? The cosine. So when I use that logic here, when I take this vector and break it down, I'm going to have a normal component in this direction. I'm going to have a value in this direction going down, because to get from here to here, you have to go down and to the right. And the x value is going to be the weight, which is mass times gravity. Instead of cosine, is going to become what? Sine of theta. And this becomes what? Mass times gravity times cosine of theta. So backward. Again, the reason for the backward, because the angle is really with respect to the y-axis, not with respect to x. We said you're going to move which direction? In the x direction. See that? I pointed out. You're going to be sliding down. So you're going to be moving in this direction. So let's see. The net force equals mass times acceleration. The net force is this one, mg sine theta. Equals the mass times the acceleration. What will happen to the masses? They cancel each other out. What is the acceleration of that person going to be? G times sine of theta. So you tell me what the angle is, and I'll tell you how fast you're going to be moving. I know gravity is 9.8. If the slope is 30 degree slope, you're going to be moving at G, which is 9.8 times sine of 30. If that's a steeper one, 40 degree, will be 9.8 times the sine of 40. So that's how fast you're going to be sliding. The steeper the hill is, the faster you're going to be going, the larger the acceleration. The flatter the hill, the less acceleration you have. The two forces here will cancel each other out. There's only two in the y direction. You weren't bouncing up in the air back and forth. You were staying on that slope, gliding down. So in this direction, the y direction, you were not going up and down. So that means this one equals to that. But that's what you have to remember. When you're on a hill, the value in the y direction is always going to be, or in this direction, not in the y direction. Coming down here is going to be the mg sine theta, and the weight this value in this direction of the weight is mg cosine. So you're not going to see me even draw this line soon enough. I'm just going to put mg sine this way, mg cosine, because that's what these two numbers are. Okay. Question on this, Jason? No? I wasn't sure. I saw your hand up there. Yeah. Now, the last thing I want to mention here, then I'll close this chapter. We go to the lab and do something similar to what we're talking about here, Newton's law, is the apparent weight. What will happen to you if when we go to the 6th floor, you jump in the elevator and whoop, what do you know? There's a scale there. And I said, get on the scale, let's see how much you weigh. If the elevator is moving up or down, does that change your weight? It sure does. If the elevator is not moving, or it's moving at constant speed, if there's no acceleration, your weight is going to be accurate. So if you're in the elevator, initially the elevator is not moving, it's going to pick up some speed. Then once it hits a certain point, it moves at constant speed. During that time at constant speed, your weight is exactly the same if it will be on the ground here. But when it starts to slow down, to stop there, you have a deceleration, your weight's going to change. The same thing, when the elevator starts to move up initially, your weight is not going to be the same. That's called apparent weight. So let's look at that topic there quickly. Let's say we have, what are we going to hang in the elevator? We're not going to put a human. So we have a chicken, a 5-kilogram chicken. We're going to be frying a chicken in the elevator. We have a 5-kilogram chicken hanging from a scale there. So there's my scale here, and this is my chicken hanging from it. Well, chicken doesn't have legs here, 4 legs. Let me throw a chicken here. Looks like a duck, but that's okay. And the scale says, we got 5 kilogram here. It's an elevator. We're standing inside an elevator. The elevator is not moving now. What is the apparent weight? That's when, here we go. The first question, A. What is the apparent weight? What the scale is going to tell you, which is not the real weight actually, but what the scale is telling us. Of the chicken so we'll call that WA. If the elevator, well, you know what, let's do this actually instead of A here. We'll just make that one question. What is the apparent what is the apparent weight of the chicken if, part A, the elevator is at rest? We'll do it this way. At rest. Part B, moves with upward acceleration. Upward acceleration of 2.5. C moves with a downward acceleration of 3.2. Want to take a guess? When do you weigh more? When do you weigh less? Is it on the way up or on the way down?
More on the way up.
When elevator is accelerating on the way up, then down?
I'm
Okay.
just thinking because there would have to be more force pushing up, right? If you're
Makes sense.
in the elevator. as
Yep, the
opposed-
floor, the elevator floor is pushing harder on you to push you up. Makes sense. Let's see. Let's see if we're right. Okay, if the elevator is now moving at rest, I got it. That's right. I know you want to stab me. Part A, if the elevator is at rest, we have the weight of the fish, and the scale is pulling up. If you look at the fish, actually, what do we have on the fish, acting on the fish? We have the weight of chicken, not a fish here, right? That chicken became a fish here. So when you look at it, we have the weight of the chicken, which is what? 5 times 9.8, mass times gravity. And this will be what? 5 times 9.8, that's 49 Newton. And we have what the scale is telling us, which is the apparent weight. Remember, the chicken is attached to a string, and that string is attached to the scale, and the scale says that's the apparent weight, what the scale sees. So for part A, the net force in the y direction is equal to mass times acceleration. Now the elevator is now moving. You want to use up as positive, down as negative? So the net force is going to be WA minus the 49, right? Up is the plus, down is the minus. That has to equal to the mass times the acceleration. What's the mass of the chicken? 5, and what's the acceleration? 0, it's not moving. Can we do the math? What is the apparent weight of the chicken? 49 Newton. What was the real weight of the chicken? 49 Newton, if you weighed it on the ground. And by the way, that's the same if the elevator moving at constant speed. So even if the elevator is moving at constant speed, your apparent weight will be the same. Why? Because if the speed is constant, what's the acceleration? Still 0 acceleration. That doesn't change. Part B now. The elevator moving upward direction. Okay. The net force equals mass times acceleration. The net force, I'm using up as positive, down as negative. The apparent weight minus the 49. The apparent weight is the string pulling up on the fish to the scale, right? Minus the weight of the chicken, which is 49. It should equal the mass times the acceleration. What's the mass of the chicken? Mass is what? 5. And what's the acceleration? When it's going upward, is that positive or negative? Positive 2.5. Is that 12 and a half?
Mm-hmm.
And what is the weight, apparent weight on the scale?
61.5.
61.5. So notice you just gained some weight. So if you get in the elevator and it's moving upward, yes, Jason, go ahead.
Oh, sorry. Where does the 2.5 come from?
The 2.5.
On B?
Oh, right here.
Okay.
The elevator moving upward with acceleration of 2.5. Upward means plus acceleration. We're using up is positive, down is negative. That's why we made WA positive and the 49 negative, because the 49 is down, the WA is upward. Now part C here, if it moves downward, still the same equation. The net force in the y direction equals mass times acceleration. The net force in the y direction is what? WA minus the 49. WA pointing upward, the 49 pointing down. Should equal the mass of the chicken, which is the 5, and the acceleration. Since you are coming downward, your acceleration will be what? Negative 3.2. Is that negative 16?
Yep.
You move the 49 to this side. What's negative 16 plus 49? 33? Boy, I lost a lot of weight quickly. So when you get in the elevator, if the elevator is not moving or moving at constant speed, your weight is going to be, or in this case, the chicken's weight is 49 Newton. The minute the elevator starts to go up at that, because all elevators set up the same way. Like if you're going from the first floor to the 10th floor. Let's see, when I go from the first, this is the first floor, this is the 10th floor. You get in the elevators, it's not moving. Your speed is 0. It's going to pick up some speed up to here. There's an acceleration, positive acceleration here. Then from here to there actually moves a constant speed right there. If it's constant speed, that means what? Your acceleration is going to be what? 0. Now you're moving, let's say at 4 miles per hour, you're going to bring it to 0. That means you have what? A negative acceleration. So this segment here is going to have a negative acceleration. So on the way up, at the beginning, your weight is going to be heavier. Then it's going to go back to normal. Then it's going to decrease there. And if you're coming down, the reverse is going to happen. You're coming down with acceleration in this direction, that's negative. So you're going to weigh less, same, and here will increase actually. And that's what will happen if you're watching your weight in an escalator or elevator there. Okay.